All right, welcome to our next lecture video here for Chem 161, Chapter 1 content, and we'll be discussing phases of matter. Okay, so to start, let's consider a container that I'll just cartoon here as a box, and we'll put a solid object within it. Okay, so that solid object might look like this. Okay. And so hopefully you know some of the properties of a solid is that a solid is characterized by its rigidity. It's known to have fixed volume, and fixed shape. So that is to say, this black solid doesn't distort under the forces of gravity and kind of occupy the bottom portion of the container. It retains its shape, and obviously its volume is also constant. Now, as we consider the next state of matter, the liquid state of matter, it's possible that this same object could transition into that physical state of matter. And so this next one would be the liquid. Here, and liquids are known to be relatively incompressible. And they don't have fixed shape. So that is, they will flow and take the form of the bottom portion of a container under the forces of gravity. Okay, and then our last container here might be for our third physical state of matter, which would be, of course, the gas. Okay, so notice here I'm using a lowercase g in parentheses to indicate that physical state of matter. In the previous version, we had a lowercase l, again with parentheses to indicate that. And in this case, the cartoon for what this would look like is now a lot of space is installed between particles. Particles could be atoms or molecules, depending on the material. And these would flow and occupy the entire volume of the container. So our little black particles representing either molecules or atoms have expanded and put a lot of space between those particles, and now allowing that gas to occupy all corners of the vessel. Okay, so these are known to be quite compressible. Materials, and they will not have fixed volume or shape, so no fixed volume or shape. So that is, going back to our liquid, makes sense that we could say that the liquid here would have a fixed volume, given that it is quite incompressible. So we can change the volume of this gas by compressing it. So hopefully that helps you there. Okay, so those are our physical states of matter: solid, liquid, and gas. And notice we've used some of the symbols there. So let's put a couple of comments here. So we've seen in the discussion of this arbitrary solid that we've said that the material might transition between the two. So that is, we might be able to change the solid into its liquid form, and likewise that liquid ultimately into its gas form by applying heat, for example. So this would be a physical change. And so a physical change is changing phases is a physical change. Okay. And so we note here especially that the state of matter is changing, but the substance is the same. Okay, and what we mean by that last part is that the connectivity of atoms in the particles is the same. So if it were a molecular compound, the bonds that are holding certain atoms together is still the same, and molecules can ultimately move away from other molecules to allow the material to flow and occupy the bottom portion of the container. This would be characteristic of the liquid, or even the space between molecules can increase, and this would allow for this physical state of the gas. But again, the main architecture of the molecule would be the same. No bonds are breaking or forming as we go between these physical states for a physical change. Okay, looking at that more carefully with an example we're familiar with, we can consider water. So we're familiar with water as either ice, liquid water, or steam. And to use our phases of matter symbols, we would use H2O, and in its ice form, we would indicate that that is the solid with a subscript lowercase s with parentheses there. And we could distinguish that from liquid water with the same formula for water, H2O, and use a lowercase l with parentheses as a subscript on the formula for the compound and indicate that that's a liquid form. And finally, the steam would be, of course, the same formula here, H2O, but we would use the gas state here. So notice that the chemical formula, the H2O, is the same in all three of these cases, and that's indicating that there is no chemical change here because the conductivity in H2O is the same across all of these phases of matter. Some other terminology that you're familiar with is how we describe the transition from one to the other. So we know that we can move or turn ice into liquid water through the process of melting. The opposite process would be freezing. Because no new bonds have formed or none have been broken, we can do this reversibly as much as we want. And if we heat further, we can transition liquid water into steam. Okay, so we would undergo the process of vaporization, and we can transition steam back into liquid through the process of condensation. And with the conditions being just right, we can even transition from the two extremes here, that is, take ice directly into steam using the right combination of pressure and temperature. And so this would be the process of sublimation. And vice versa, taking steam directly back to its solid form is known as the process of deposition. All of these transitions of one physical state of matter, of this case water, are physical changes, and again, no chemical changes happened, and that's reflected with the chemical information in the formula. There's another symbol like this that we need to put a little bit of attention to, and that is for situations where a species has dissolved into water. Okay, so we note the condition for aqueous solutions, and what this indicates, aqueous indicates dissolved in water, sometimes often referred to as solutions, periodically for shorthand, scripted as such, SOL with a superscript N for shorthand. And we'll show the importance of distinguishing all this, and the symbol for this, by the way, is going to be lowercase aq with the parentheses. Okay, and so let's consider NaCl. This is the ionic compound that is known to be present in table salt, and so we can consider NaCl aqueous, which would indicate that salt has been dissolved in water. This is a physical change and not a chemical change. So that is, the sodium ions that are present in the table salt granules are still the same as the sodium ions that are dissolved in the water. So there's been no kind of chemical process there. So it's still the same species. And so that's how we identify this as a physical change. Dissolving of NaCl into water is a physical change. Let's contrast this to some other common mistake that we see sometimes, which is NaCl liquid. So while the solution of water and table salt is in fact a liquid, we also call that a solution because we know that there is dissolved species present. NaCl liquid does not describe that aqueous NaCl. NaCl liquid is indicating a situation where we have melted salt into liquid salt. This takes a lot of temperature. If you've ever experienced salt in a heated pan on your stove, you have never been able to melt NaCl on your stove because no stove can heat salt to its required melting temperature, which is approximately 1474 degrees Fahrenheit. Okay, so notice the difference here. NaCl with a subscript of parentheses L is indicating the molten salt, very hot conditions for that. Whereas NaCl liquid, this is something you can do even in your fridge, where you ask table salt to dissolve and dissociate into water without undergoing chemical change. Okay, very good. So that's our quick introduction to some of the terminology and discussion on physical changes.